Hi, in this video we are going to talk about another strongly connected component related algorithm, the so-called Tarjan algorithm. Of course, the aim of the algorithm is the same as we have seen for Koszary algorithm. We would like to end up with strongly connected components. In order to understand Tarjan algorithm, we should consider forward edges, backward edges, and cross edges. So let's suppose that we have a graph like this with directed edges. A forward edge is something like this. A cross edge is something like this. And the backward edge is something like this. Okay, so there are three types of edges: backward edges, cross edges, and forward edges. So Tarjan algorithm runs in linear time. We use a depth-first search again for traversing the graph, as we have seen for Koszary algorithm. But we have a very important fact, the so-called stack invariant. When depth-first search recursively visits a node V and its descendants, those nodes are not necessarily popped from the stack when the recursive call returns. A node remains on the stack after it has been visited if there exists a path in the graph from this node to some node earlier on the given stack. So this is the stack invariant, that sometimes nodes are not going to be popped from the stack when the recursive call returns. So at the end of the call that visits V, we know whether V itself has a path to any node earlier on the stack. If yes, which means that V has a path to any node earlier on the stack, the call returns and V stays on the stack. If no, so V doesn't have a path to any node earlier on the stack, then the V node must be the root of its strongly connected component. And basically every other item on the stack is the part of that given strongly connected component. By the way, Tarjan algorithm is very hard to grasp as far as the theory is concerned. We are going to implement it together with lots of debug comments to the console, and I think it's going to be clear. Okay, so it's very important that for Tarjan algorithm we have two parameters, the index and the low link. In our implementation we just have the low link because the index is the integer we assign to the nodes consecutively in the order they are visited by depth-first search. The low link is the smallest index of any node known to be reachable from node V. Okay, we are going to implement it, so I'm not going to talk about it. What's very important that if the low link is equal to the index, there is no backward edge to any other node, so the current node is the root of a strongly connected component. If the low link is smaller than the index, it means that we have found a backward edge in the given graph. But as I said earlier, we are not going to use the index in our implementation. So for example, we have 7 vertices, 1, 2, 3, 4, 5, 6 and 7, and it is a directed graph as you can see. We start at a given vertex, for example the vertex 1, and recursively we use depth-first search to visit every neighbors of that given vertex. It has a single neighbor, the vertex 5, so we consider vertex 5. We consider every single neighbor for vertex 5, which is the vertex 2 basically. And the vertex 2 has a single neighbor, the vertex 1. But we have already visited the vertex 1, so we can come to the conclusion that this 2, 5 and 1 consists the first strongly connected component. Then we consider other vertices of the original graph, for example 6, and we recursively visit every single neighbor of that given vertex, then the neighbors of the neighbor of that given vertex and so on. This is how depth-first search works. It's going to go as deep into the graph as possible. So we visit recursively 3, then we visit recursively 4, and 4 doesn't have any unvisited neighbor because we have already visited 3. So it's going to be the part of another strongly connected component. 3 is the part of another strongly connected component. Okay, but as you can see, we are not able to reach any more unvisited vertices because we are not able to reach the 7. We are able to reach 2, but we have already considered 2. 2 has already been considered to be the part of the green strongly connected component. So we can come to the conclusion that the second strongly connected component contains only 2 vertices, 3 and 4. Then we have the 7 on the stack and the 6, and again we can come to the conclusion that they are part of a different strongly connected component. So there are 3 strongly connected components in this graph: 1, 2, 5, 3 and 4, 6 and 7. So we are able to find the components with the help of Tarjan algorithm. We just have to define another parameter, the low link. This is what we are going to implement in the next video. Thanks for watching.